Alright, welcome back, Digital Electronics. We're going to be going through flip-flop applications. Today, last lecture, we talked about the D flip-flop and the JK flip-flop. Now we're going to talk about, how we can actually use a flip-flop, in a circuit. So, different applications that we're going to talk about is event detect, data synchronizer, alright, a frequency divider, and a shift register. Okay, we're going to talk about using them as a counter and things like that in state machines a little later on in a couple of future units as we go through here. But let's talk about what an event detector is first. All right, so what an event detector does is it detects an event and it grabs and holds that signal until you change that signal yourself or until the event can be addressed. So we have example in here, door sensors on a home burglar alarm, right? It detects that someone breaks into the house or the glass breaks, someone opens that door, the alarm's going to sound until the system is turned off. All right. Same with something like a fire alarm at your house or things like that. Your smoke alarm. All right. It's going to sit there. It's going to detect smoke and continuously go off until you go reset it. At school when we have a fire drill or a real fire for that case. All right. The fire alarm goes off. Alright, consistently it has an audible and it has a visual, right? And the only way for us to, stop that from continually going off is someone has to go reset the alarm. So that's an event detector. It detects the event that's going on and then it holds that in until someone does something about it, okay? So if we do a single event detector, okay, we can use our flip-flop here because remember flip-flops are memory. So we can hold the event. So really what happens is the event is the clock signal. So remember the flip-flop can work on the rising edge of the clock. So as long as, our preset there is sitting at 0, and then when the event happens, the clock edge rises, and what happens is Q follows D. So look at what D is. D is wired directly to 5 volts. So D will automatically turn on the rising edge of the clock. And that's going to be held, okay, until we clear out that the event happened and then everything is good. So this is how we can use a D flip-flop to hold and detect a single event that's happening until we clear it out of the system. All right, so that single event happens, that's the clock signal, all right, and then it holds that event until we hit the clear. The second we hit the clear, that event stops. So anytime the event triggers it, all right, it's going to stay and produce the output, so a beacon alarm, a light, anything like that, until we hit clear. And clear has to be pressed or reset, right? Essentially to, remove that event from memory in the D flip-flop. So you can study through a couple different cases here. So we can take a look at, how multiple events can keep occurring, but if we don't clear that first event, so I'm looking at case 2 here. So if we don't clear that first event and, say multiple fire alarms start going off throughout a building, okay, they're not going to trigger anything new. That event's just going to stay going on until someone clears it. Okay, so that's how we do event detect and how we hold that signal. All right, now we can start talking about data synchronization. All right, making everything kind of be, happen all at the same time. So timing's not a big concern with our combo logic, right? But if we have gate delays and things like that, it can affect, we saw like the ripple effect with, 7-segment displays or things like that. So you want to make sure that we don't have timing problems. So what we can do is synchronize all the data so it gets the clock signal at the same time. So we can use it to synchronize data so we don't get that event. So if we take a look, this is still looking at a D flip-flop here, 74LS74, and notice if we tie all the events to the same clock signal, we are synchronizing all the data at the same time. It's kind of like the movies where you see them like everybody synchronizes their clocks at the same time. You're going to synchronize the data at the same time. So when the clock signal rises, it's going to rise for all 3 flip-flops at the exact same time. So you're synchronizing the data. That's really the difference. The flip-flop's still holding the memory, but when they're all tied to the same clock signal, everybody's going to change at the same time. So, here's what it's going to look like if we latch that signal in. All right, everybody's going to go on the rising edge of the clock. So, A might be wherever it's at, B is going to be where it's at, C is going to be at. But when the clock hits that rising edge, okay, everybody's going to do what they're supposed to be doing. Q will follow D for each one of those scenarios, A, B, and C. Okay, it just depends on what D was. All right, this is a common one that we're going to do in here. We're going to do a frequency divider, and this is the one piece that we touched on, earlier in the year when we started doing the divide by 2 circuit. Okay, when we started adding multiple flip-flops in a row and connected to each other, so we can divide the frequency in half. Okay, so we can really draw that out, and that's how we used it as a counter. What we're going to use later on. So we can go 0, 0, 0, 0 all the way through 1, 1, 1. So we're going to get to that again when we do our asynchronous counters in a future lecture. But that we can use it as a frequency divider. So we can use a JK or a D flip-flop to do this, and it just depends. What's really going to help us with the count here? If we look at the D flip-flop, all right, we're using a closed loop type system here. Notice what's different with the flip-flop. So we're using itself, okay? It's kind of like self-excited as it goes through. Our Q naught becomes our new D. So that's what's going to be our driving force. So when we used Q naught as D, all right, we're using its feedback, all right, to replace itself. So when the clock comes in, our divide by 2, notice that we are, the period is twice as long. And then the more we add, all right, and we divide that signal by 2, and then the next signal by 2. Okay, so that's how you set those up. Notice if we want to do that with a JK, all right, we wire both of them to 5 volts. Because remember what happens when JK are both 1, right? 1 and 1, that was a toggle event. So that's automatically going to do that for you on rising clock in on your JK flip-flop. Okay, and we talked about that last lecture. All right. This is just a review of the frequency divider, right? When we talked about periods and different things with time, frequency, duty cycle, all those different things we talked about before. But remember, the period is from one rising edge to the very same rising edge at the next time. So if we look at clock in, that period is T1. All right, it goes up, down, and then back up. So it's where it's rising edge to rising edge on our clock in. So the period of our clock out, all right, is going to be twice as long because we divide it in half. So it really takes 2 rising edge times to our original one, if that makes sense, okay? So that's why it's divided by 2, because the period T2 is twice as long as the period T1. So that's how we do our divide by 2. Okay, using itself for feedback. And if we want to string that out even longer, we add more flip-flops in series with one another. All right, let's talk about a shift register. What a shift register is going to do is it's going to take our stored values in our flip-flop, and it's going to shift them through kind of an array of flip-flops. So if we have 3 or 4 flip-flops in a row, okay, it's going to shift it. It's going to shift the signal down each time. So every time, if it's going to shift through like 0, 0, 0, then it'll shift through like 0, 0, 1, so on and so forth. And that value kind of cascades down through the D flip-flops. Okay, so when do we use these? Well, we use them in controlled digital displays. So if we want a whole bunch of 7-segment displays to turn on, we're going to use a shift register. All right, so we want to be able to, like, on our FPGA boards, if we want to turn on, all 4 or all 8, 7-segment displays at once and shift logic data through them, that's what we're going to have to do, is use a shift register. All right, another example is numbers being typed into a calculator. Okay, so as the numbers are entered in, right, the digits shift to the left 1 position. So every time, think about this, next time you're punching numbers in your calculator, you're just doing some simple multiplication or things like that, you're really applying a shift register to what you're doing. Okay, so what's happening in? All right, so if we have that serial data in, remember serial, we can transmit that 1 bit at a time, and as that goes in, all right, left to right, the data in, all right, and then we can have it come out data out. So, think of more like a counter. It's going to shift this one in, and then it'll shift the next register in. So, we might be counting up. So it might go like 0, 0, 0, and then it might go 0, 0, 1, and then it might cycle to 0, 1, 0. Okay, so we're shifting in one at a time, shifting out one at a time. If we do parallel, all right, parallel means that we can send in a whole bunch of data at once and then send them in chunks that way. And we'll get into more things like serial and transmission, parallel transmission, USB transmission. That'll be more in an advanced digital electronic fundamental course. Okay, but for us, just kind of understand how it's going with data transmission. So what a shift register would look like this. Notice they're synchronous, right? How do I know that? Because they're all connected to the same clock. Okay, so the clock signal will be the same so that everybody shifts data at the same time. But notice how we're sending the data through. So we send in whatever data we want, okay? And then what happens? The output, the Q of our first flip-flop, is our input for our next flip-flop. And then that second flip-flop, its output Q is the input for the third flip-flop. Okay, and then the Q that comes out of that third flip-flop is the input for the fourth flip-flop. So that's how we're doing our data shift. All right, we're going to have a synchronous clock signal, so everybody shifts at the same time, and then we're just going to pass whatever data that we originally started in. Okay, it's going to pass through and get to the last flip-flop, but it's got to go through the second flip-flop, it's got to go through the third flip-flop, and then it gets to the fourth flip-flop as we sent that in. Okay, so that's what a shift register is doing. Notice we don't care about the Q bar signal at all in this case. We're only really paying attention to the Q signal, so as that goes through. Alright, so we shift our data through one step at a time when we do this. Alright, here's what it looks like if we have a JK flip-flop. Okay, so what are we really doing? Well, for us to shift this data in, we're going to be driving, okay, J is going to be driven with the Q, and K is going to be driven with Q bar. So we're going to invert K originally. All right, so our data might come in as 0, 1. So we had to remember what 0, 1 did with our JK. What did it do? Okay, as it's not the toggle command, but it would send the high in if we had that scenario. Okay, so it's going to lock that. Notice still with all of these, we still have the same clock signal. So everybody's going to shift, okay, on the falling edge on this one, right, or the rising edge. Depends on, where we're going in. But notice there's a bubble in front of this JK. So that does make a difference when the clock signal is inverted. Okay, so notice we have the 5 volts and the clear going to 5 volts is going to preset and clear for all these, just like it was here on the D flip-flop as well, because remember that those are inverted because of the bubbles. Alright, so there's how we would do a shift register using a JK flip-flop. And we talked about JK flip-flops in the last lecture, so we should have an understanding. But as that shift register goes through, right, we're transmitting that data in, alright, and D0 is where it goes through the first flip-flop, D1 is through the second flip-flop, D2 is through the third flip-flop, and D3 is through the fourth flip-flop. And notice it happens on every rising edge of the clock, or I'm sorry, not rising edge, the falling edge of the clock in this case, okay, because this is for the JK flip-flop, okay? So we're doing this one on the falling edge, and how do I know that, right? If I flip back here, the bubble before the clock tells me it's a falling edge. Okay, so that's what our shift register is. We're shifting that data through from our our LSB, our least significant, all the way through our most significant bit. Okay, it's very important that we understand that. Now we have a special chip that can do that for us for medium scale integration, right? MSI. We have a 74LS194. Okay, so we can have 4 parallel inputs, A, B, C, and D, or we can have a couple serial inputs. We can have our mode control, and we have our clear and our clock. Okay, so I'm not going to spend a ton of time with the shift register chip and things like that with us, but I want you to know that it does exist. You'll use this maybe more in some advanced engineering. We're going to focus in our class more on getting the flip-flops and then understanding our D flip-flops and making sure that we can cycle those through. But you can figure out, going through this table here, exactly what our outputs are going to be. And you'll probably do one of these in lab, and we'll do the shift register. All right. You're going to be also doing the shift register making with D flip-flops as well, not just using the 74 LS194. But we can see how we can control this in. And this particular case right here that we're looking at, that's set up for a serial. Okay, so we can send in, all right, either, our 5 volts or our ground. So we're going to send in a 1 or a 0. Our clock is still going to go, as it has been, high, low, high, low, high, low, constantly. Okay, but we're going to send in a specific signal. So you're going to do this in a lab using multi-sim. Okay, and you should be able to understand where the shift register is. Okay, so now instead we're going the other direction. Okay, I know it looks flipped. We're on the rising edge of the clock on this case. This is tied specifically to this chip. Okay, so if we were to run this through here, this is exactly what's going on. Okay, so our data in, I'm going to step back here. Our data in is us hitting the space bar, right? Going either 1 or 0. Okay, and then we're going to see what happens with X1, X2, X3. Well, on the rising edge of the clock, because that's how this one's going to be. Even though there's a bubble there and it's inverted, we're still doing rising edge because it's how the chip is. Okay, and it will be, you see where X1, X2, X3, X4 all toggles through. Okay, we can see where X1, X2, X3, and X4 are. Okay, where X1 is our MSB, X4 is our LSB. All right, that's the one that's going to be changing. Everything's kind of switched opposite here when you do these. Okay, so as it goes through, we'll be able to do this, and this will make a lot more sense, guys, in class when we actually make the lab and you guys run through this. But that's the end for this class, and like I said, we're going to focus a little bit more on the D flip-flops and things like that. But you guys will build these in multi-sim, work through some labs. That'll really help you with gaining an understanding of what we're really doing here with like event detect, shift register, counters, doing all those different things. So, else guys, this is the end of the lecture. If you have any questions, email me. Let me know if we need to Zoom meet or team meet or anything else like that. Else guys, I'll see you in class for that.